is titled From Ambiguity to Precision, a framework for specifying post market surveillance requirements for AI enabled medical devices. I am Saakshi Sharma, and this is my submission for SIT217A under the domain Safety Critical Systems. Let me give you the scale of the problem. Between 2020 and 2024, the FDA approved 100 times more AI medical devices than it did in the 2 decades before. Yet, 43% of those devices are recalled within the very first year, twice the rate of the traditional devices. The TruDi surgical navigation system is the case at the center of this research. Before AI, it had 7 malfunctions over 4 years. After AI was added, the malfunctions jumped from up to 14 times. Patients suffered strokes and skull fractures. The FDA issued a Class 1 recall. And one plaintiff even said that the product was arguably safer before AI. The root case was not bad engineering, it was that the FDA told the manufacturer to monitor device performance without specifying a single metric, threshold, or frequency. Then, the proposed solution to this is a hospital embedded ML surveillance model that runs within each hospital's own network. On the left, you can see the 3 layer architecture where the first layer is collecting the anonymized performance data from AI devices and clinician incident reports and the FDA mod adverse event records. The second layer is processing the data using a random forest drift detector, which flags the statistical deviations, and there is a trend analyzer tracking the gradual performance decay over time because the failures of TruDi did not happen overnight. They accumulated slowly. Both of them are feeding into an alert engine, which is then generating a real time dashboard, and the third layer is delivering the email alerts. Then on the right, there is a fishbone diagram which shows exactly why the system is needed. 6 root cause categories from vague regulations to human underreporting, all pointing to the same outcome: AI devices failing after they reach patients. Then, this is the context diagram for the system, which shows who interacts with the system. Then, there are the 12 requirements. The core contribution of this work is these 12 fully measurable requirements. These are derived through a 4 step process combining the fishbone root cause analysis, the risk classification, and the regulatory traceability, along with the validation against a clinician persona. Each requirement has an acceptance criteria which tells you exactly when it is satisfied. Where the FDA says monitor performance, requirement 1 says log accuracy sensitivity and specific every week with timestamps and sample size. Where the FDA says nothing about the drift, requirement 3 says trigger an alert within 24 hours when the accuracy drops more than 5% over 30 days. Where underreporting was a documented failure in TruDi, requirement 5 says incident reporting must be completable within 3 clicks. Every requirement is traceable to a regulatory source and to a real user need. The framework then delivers these key performance metrics: a 95% drift detection accuracy and an alert delivery latency, 12 fully measurable requirements, and an assurity of incident reporting within 3 clicks. Now, regulations will always be written in natural language. They will always be imprecise. That is not a flaw, that is just how the law works. But between the regulation and the patient, someone must translate monitor performance into a number, a frequency, a threshold, and an alert. This framework is that translation. 12 requirements, fully measurable, and built specifically for systems that are already inside our operating rooms, whether we are ready for them or not. Thank you so much.